Hello everyone, welcome to the second session of MATLAB tutorial in MTE203. And for this course, we're going to introduce the basic 2D and 3D plots. First off, let's start introducing with line space. Line space makes an array of values that are linearly spaced. You can, if you don't understand how this function works, you can basically type in help line space in MATLAB. And a brief demonstration of line space, you can do t equals to, say, line space. The first is the starting, and the second argument is the ending number, and then the third argument is how many numbers or how many points you wanted to create, say 100. Then you'll create a 100 values of array, which starting from 0 and ending to 1. Okay, so they're equally spaced. And you can also display the variable by this t, which will display the variable. And the other part, this is 1D. So in 2D, you can have mesh grade, this function. The mesh grade generally accepts a 1D array. Say, since I already have a 1D array, t, I can create, based on that, create a 2D array, say x mesh and y mesh equals to mesh grade t. And after hitting enter, I can observe that I already have a 2D array, which one is x mesh, the other one is y mesh. Okay. Based on the x mesh and y mesh, let's create a 3D plot, because I already have something in 2D, right? So I can create a surface plotting based on that. So basically, creating a surface plotting, you can do z equals to fxy, right? So the general idea is, given the x and y, you have a z. This is a 3D plot, or this is a surface. So let's starting by creating something similar. So let's do, say, since I already have x mesh and y mesh, I can do a function z equals to, say, exponential of x mesh. Let's do the exact same with the PDF version. So square root 2 minus y mesh square root 2, okay, and plus 10 plus 1. Okay, let's do a little bit change. So the general idea is the x mesh is what I created in x, and y mesh is what I created in y, and so these two are discrete numbers, and I do the x squared minus y squared and exponential and then plus 1. So this will be created z. Okay? So now I created a z, which is 100 times 100 double, and what I need to do is just plot it. So how do I plot a 3D surface in MATLAB? You can do surf. So what does surf do? You can do help surf. So the surf basically plots the colored parametric surface defined by 4 matrix arguments. So the general idea is passing to 4 different arguments. However, some arguments can be dismissed. So you can directly using surf z and surf zc, so that the c basically means the color scaling. Okay, so if you're using the default color scaling, you can directly using surf z. So I can passing surf the z, which will generate a plot. So this plot is what we just created. The surface of that function we just created. You can toggle that or rotate that by using the widget here. You can toggle that until you find it's quite clear. You can also do a zoom in and zoom out, or you can just move it around with the widget here. Okay, that's it for surf. Also, there are many other helpful commands you can find in the PDF version, such as ND grade. It's very similar to the mesh grade. We'll just skip that. The other thing is you can redefine the color map using the C argument here. It's also mentioned on the PDF version, so we'll just skip that. Okay, let's move on to the next part. It's a contour plotting. For example, given, say, let's do V equals to line space. So the general form, I'll clear everything in the CLC. The general form of 3D plotting is first you create a 1D array. Say V equals to line space, say -10, the ending will be 10, I have 100 points. So the idea of creating 1D array is using that to create a 2D arrays, right, for X and Y domain. So you'll further create X and Y, these are discrete points distributed in XY space. And this will be created based on mesh grade of V. Okay? And then further on, since you have discreted X and Y, you can, based on that, to write a function of Z. So I can say Z equals to, say, cosine X in here times sine Y. So this will be a wave, like it's more like a function of a wave. So we can find it, how does it work, saying surf Z, and we'll find, oh, in 3D it looks something like this. It's more like a wave, and you can move that around. You have the up and downs, right? So when you looking here, it's more like a contour plot, right? So if I wanted to plot the contour, how do I do that? You can do that by typing to the command of contour Z. Oh, here, CON, yeah, it's not a COU. So CON, where you have the contour plot like this. However, you might be very confused of how does these color means, right? So the other very useful command is color bar. So after typing color bar, you will have a nice color bar just adjacent to your original plot, where it indicates what color, what value of that color is. For example, here it's obvious where the yellow ones are larger values and the blue ones are negative values or lower values, right? And that's for the contour plot. The next part is numerical equation solving. So in many cases in your MTE203, you'll find some vector functions and you're trying to solve that vector function. Or in other math courses, you have to solve some functions. MATLAB obviously has the ability to do that, to solve a function. So the command here is to use fsolve. It's a function solve, abbreviation of function solve. So what does this fsolve need, or how do we find how to use that? You can type in help fsolve. You'll find here there's a long documentation. However, it says fsolve solves systems of nonlinear equations of several variables and attempts to solve equation of the form where fx equals to 0. In many cases, you have some functions, say a function of velocity, function of acceleration, function of any vector form, and you may find, say, when does it become 0, or a function of a curvature, when does it become 0. And in order to find that specific x, you can use that fsolve function, right? And in fsolve function, there are two arguments. In most cases, you can use two arguments directly to use fsolve. The first argument is a function fun, so you have to pass in the first one as a function. The second one is the initial guess, x0. So x0 is the initial guess of your solution. Okay, let's write a very simple function. Say function here, I have the output is y, and the function name, we call it fun function, and it passing one argument x, and the function result is y equals to x squared. Okay, so that's our function, and we remember the last time we need to save the file as the same name, right? So we save it as fun function. Now in the current path, we have fun function as our function file, and the name is the same. Okay, and we already know that for this function, in order to have the final solution of fun function equals to 0, which means the explicit solution to that will be x equals to 0, right? So y equals to 0 as well. So in that case, we already know the answer. We can do x and value. This x will be the expected resulted solving solution of x, and value is the expected value of y. Now we pass into fsolve. So we use this function fsolve to solve our function. And the first one, in order to tell the MATLAB it is a function instead of any constant or any variable, we have to pass in the at notation. And at, now we pass in the function name, fun function, and use initial guess. So let's try out if we our initial guess is far away. It is totally biased. Say 100. So it's let's say 1000. It's like 1000 away from the initial solution. And now we can have is the final solution of x, and the value. The x is 0.0045. The value is 2 point something. So here is we can go back to the original documents. So here MATLAB using the numerical solvers to find the solution. So the final solution won't be exact the same to the real solution. However, it will get close if our initial guess is better, right? So let's try another one. So suppose I have initial guess of 0.5. And now our solution getting worse. So that will be interesting. It means that the solver is not that good. Okay, so here it might have some other solvers you can use, and also other option configuration you can use. Anyway, so in this case, the fsolve is essentially a numerical solver. It won't get the exact solution to that. Let's move on to the next part. For the next part, we'll be trying to plot curves in space. We can use surf-C to plot the surface, right? For curving space, for example, in the third week or the second week, we learn parametric curves. You can define a curve. Let's clear out everything. You can define a parametric form of the curve equation based on another variable, say t. Say t equals to line space. Let's do -10 to 10. It's 100 points. And now we can define it based on parametric form where x equals to sine of t and y equals to cosine of t and z equals to t. So this is a parametric form of the curvature, no, not curvature, curve equation, right? So we have x, y, and z. So this will be a similar to a circle. However, this circle is gradually growing to the z-axis. We can plot it based on this command called plot3. So this is plot in 3D, x, y, and z. Here we have this nice form of plotting. In the real projects, in your later on projects, and any possible homework associated with plotting, you will need to add title and caption and x and y axis in your plot in order to get full marks. For here, we'll just neglect them. And further on, we move on to the symbolic math. For symbolic math, it's very useful when you're trying to define equations, and also very, very useful in the later on study when you move on to ME360 and 360 and other courses related with control systems. For example, we can define symbolic variables like sims, x, y, and z. So here, notice that the original defined x, y, and z, the arrays are disappeared, and instead they are covered by our newly defined sim variable. They're a single symbolic variable, and what we can do is say, for example, let's define y, the relation between y and x. So y equals to x squared minus 1. Okay, so here this is the symbolic relationship between x and y. They're both symbolic variables, and we can then doing factoring and solving for based on the symbolic variables. For example, we have r equals to factor. If we're trying to factor y, we can get the result, because we already know x minus 1 times x plus 1 equals to x squared minus 1. Here you use factor to factor that. And furthermore, you can do r equals to solve, say y equals to 0. Here you need to notice that this is double equal, and here is x. We can also solve that function based on the symbolic form and solve the exact solution of that function, right? This will be very, very useful in trying to find the transfer function or the roots of the transfer function in your control system study. Okay. Here, let's move on to, say, function composition, right? So, given, say, x equals to, let's do sims t. Sims define another variable called t, okay? Sims t. And suppose we have the parametric equation, say, x equals to sine of t plus exponential of t, and we define z equals to x squared of 5 plus 2. We can do expand, say z, so we can do p equals to expand z. We'll have the expand version of that, okay? Another one, since p is expanded as a very complicated form, we can also do simplify. If we do simplify of p, we can get a not very simplified version, but in some cases we can get the simplified. For example, let's do z equals to, let's copy this, square 5, and p equals to expand z, and now let's simplify p. Okay, in some cases it can guess back, in some cases it cannot. Okay, there are some inner functions behaves in MATLAB. However, for this part, I don't think we're going to use it very often. Let's move on to the final part about 1D calculus. For example, you can use differentiate and also integral in MATLAB. So in many cases, for example, in week 1, week 2, and week 3 study, we have some questions about differentiation and integral, especially in, say, finding the tangent vector, or finding the velocity, finding the acceleration, or even finding the curvature. In many cases, you can use MATLAB as a tool to make sure your answer is correct. So, for example, we can find the differentiation of the, say, z. Z is a function of t, right? So we can say z prime equals to diff of z. So notice that here z is a symbolic function, right? And diff is a function we're trying to use on the symbolic function to find its differentiation. Now z prime we can find is 5 times cosine t plus exponential of t times exponential of t plus sine of t square of 4. You can use your hand, use your pen and paper to verify that it should be correct. Okay, and since we already have a z prime, we can do an integral, right? So we do z bar equals to z prime, the integral of z prime. It will take some time, and it will appear that the z bar is the original version. However, notice that this is not the only one solution of integral, since we can always have a constant based on that, right? We can always add in a constant, so it's not the only possible solution. Okay, and that's it for the second MATLAB tutorial.